Okay, yeah, I want to talk about the infinity operads and give you, I mean, this is a talk which is based on one example, you know, and so you can, well, first this is, you know, higher structures of higher structures. If you think of operads as being higher structures, then we are going to do structures on them. So I want to motivate a little bit what's going to happen. You know, go back to the A infinity opera. This is as a warm up, or A infinity algebras, as this will be closely related. So, and I should say this is joint work with Luciana Bonatto, Safia Chettih, Abigail Linton, Sophie, Raynor, and Marcy Robertson. So an infinity algebra, which will be something familiar to many of you, I guess. This is like an associative, an algebra, which is associative up to homotopy, and up to homotopy means up to all higher homotopies. So what does this mean? It means that when it's an algebra, there's a way we can do a multiplication. If I have two elements, I can multiply them. But if I start multiplying more elements, A, B, C, I could do it two different ways using my multiplication, and these need not be equal, but I'm requiring that there is a homotopy between two such guys. Now, being an infinity algebra is more than that. It says that, well, if I start multiplying 4 elements, then there are actually 5 ways, I drew them ahead of time, 5 ways of can I do this? No. 5 ways of multiplying them, and being an infinity algebra means that I mean, my previous homotopy gives me the border of this pentagon, and being an infinity algebra means that I can also fit it in, and this keeps going with as many elements as one tries to multiply. So so this is formalized by so the structure, this structure is encoded by an operad, which is called A infinity. So this means, so A infinity is a collection of, I mean, the world of spaces. This could be in the world of algebras, if one wanted to, but I'll be with spaces. So A infinity of n greater or equal to 0. So where the n space records is n-ary, all the possible n-ary multiplication. So here I'll have A of A infinity of 1 is just a point, which is recording this one multiplication. I have A infinity of 2 is an interval, and 2, this was 2, I have 2 things, sorry, this is 3, and A infinity of 4 is this pentagon here, and so on. Good. And so maybe just let's say this is formally, so so an operad so O is such a collection in general. So again, I mean, in spaces, I have a collection of spaces, and they come with actions of the symmetric group in general. So I didn't do this for my A infinity operad here. If I did it as a symmetric operad, I should add copies for every permutation of these of the letters, and then these come with composition laws. So which tell you, well, if I have an n-ary operation and an m-ary operation, I can plug them in inside one inside the other at some place, and that's going to give me an. So this is a circle I operation. For every I between 1 and m, I'll have one of these, which lands in O n plus m minus 1. That is, I'll go, yeah, if I compose, if I do the one and then the other, I'll have an n plus m minus 1 array operation. And of course, these composition laws are assumed to be associative. and then and this is a condition that we could relax, right? Just as our composition law and our multiplication in an algebra could be assumed to be only associative up to homotopy, we could ask for these composition laws to be only associative up to homotopy. So infinity operad, these are, they're only, so like, call this A infinity associative. Okay. Right, and then you can ask, well, what does that actually mean, right? Question, what does this mean in practice? So our motivation came from a metric, so a metric graph model of the cobordism category of surfaces. So which has objects, you could say the natural numbers and stuff, morphisms would be moduli spaces of Riemann structures on cobordisms between these circles. So you can make there exist a metric graph models, but which is only where composition with only associative, only with, so whose composition is only associative up to homotopy. And then you can ask, well, is this some sort of A infinity category? Can one sort of show that actually not just this one homotopy that I can give you in every single example, given an example, I can pick some homotopy, but are there also higher homotopies? And how do I show that there are actually higher homotopies and so on? So the sort of the baby case in here, the sort of the simplest part of this question is, restricting to, if we restrict to genus 0 and call this operatic parts. Operatic. So by which I mean we're going to take, surfaces going from as many inputs as we like, but going only to one. So there may be several of these. So you can think of, something like this, which is sort of generated by something that looks like an operad. So this is like a subcategory. This graph model identifies with the category associated to an operad, which is the cactus, normalized cactus, with what is called normalized cacti. So what I'll tell you about is how this part of this category is an infinity operad. So that's my goal for today. Okay, so we need to talk a little bit about the cactus operad. I have a cactus, it's there. Okay. Yeah. So do I have enough cactus operad? So this is my cactus operad. So it's a sequence. I have a, cact is a sequence of spaces. Okay, and so the n space is, this is like a tree-like configuration of circles. The way you should think of a cactus is you have a bunch of circles that are parametrized, so they all have a start point, and they are attached together in the plane. You can think of them as being in the plane, and then you have this sort of you also have an outside start point. So you have this we have a circle that cycles. We have a sort of an outside circle, which is part of the data of the cactus. This is not a very formal definition, but it's a little bit painful to define formally. So what do we know about this operad? Well, it's a model. It's a model for framed E2, or one can make a non-framed version. So a model of an E2 operad. Its homology. So in particular, its homology. It's the BV operad, the operad of Battagnin-Vilkovisky algebras. And how do we compose cacti? So I also made a pre-drawing here. So if I have two cacti, I can take my first cactus here and say I want to compose inside the first of the two. So I do one of these circle I operation. Then what I'm going to do is I'm going to identify this outside circle here of my second cactus. I'm going to identify it with the first lobe of my so the outside circle of the second cactus I identified with the first lobe of the first cactus. And I have to say how. And how do I do that? Well, I'm going to shrink this second cactus to make it to so that this outside circle has the same size as the other lobe, and just plug it in. So in practice, I'm going to create something which is a little bit, well, there's a scaling and then an insertion. So scale composition is scale plus insert. And what we see is that this does not respect length of cacti. So let me maybe define here. And so normalized cacti. So just cact1 is a subspace of this would be subspace of cacti with lobes of equal lengths let's give them not just equal lengths, but of lengths of lengths 1 each. So where all the lobes have precisely the same lengths. Now, if I take a cactus where my lobes at the beginning have the same lengths, and I try to insert another one where the lobes also have this particular length 1, when I do the shrinking, well, I'm going to lose that property, right? So this composition does not respect. So this does not respect. Does not stay within cact1, right? This normalized cacti. But then you can say, well, but there's something else I could have done, which is just as obvious, which is to say, well, instead of shrinking my second cactus, I chose to shrink this one so that it received the same length as the first lobe. Instead, I could have decided to increase the size of my first lobe. So also do a scaling, but a scaling in scale. So the cactus composition is scale to the size of the lobe. And here you could do, instead you could say scale to the size of, scale the lobe of the inserted cactus instead. And so now this respects. So I mean, it defines a composition. So this defines a composition on Cact1. Okay, and so this is a fact of life. So this is 1 and this is 2. A fact that can be checked quite easily is 1 is associative and 2 is not. Okay, so this was already noticed by Kaufman some years ago. So these normalized cacti have certain advantages. They give a much smaller model. You're losing sort of an unnecessary scaling direction in the cacti. They don't change the homotopy type of the space. So it gives you a nice small cellular model. It's also the type of cacti that show up in this cobordism category of graphs. This normalized part is also plays a role there. But unfortunately, the natural composition is not associative, and there's no obvious way of making it, replacing it by an associative composition, if not by going to cacti. Okay, so the question, the question we wanted to address was, is it sort of a infinity? Can one fix this? Can one make a, can one use it to define an infinity operad? Okay. Good. So that leads to the next natural question is what is an infinity operad? Okay, so you look up a definition today. An infinity operad has I think what would be the favorite definition would be something like this. So it's an inner fibration to something called N-fin plus with co-Cartesian lifts for all inert morphisms and then such that O of n is, so there's a sort of O of n is isomorphic to O of 1 to the n, and the morphisms from in O from n to m identify with a product in m of morphisms in O, F inverse, I'm almost done, F inverse I to 1. Okay, so this is sort of what a modern definition. So would say, if we could try to unpack roughly what this means, well, i.e., roughly you have O, which is an infinity category. So some sort of category up to, I mean, you choose your model, but some sort of infinity, some sort of category A, some sort of A infinity category. And what the definition is saying is that this A infinity category, that looks like, that is basically like what used to be called the prop. Oh, I would still call the prop associated to the operad. That is, if you have an operad, just as we saw earlier with this cobordism category, you can define a new category with objects, the natural numbers, and then your morphisms from n to m would be, you're going to take whatever, 1, 2, 3, 4, 5, 1, 2. I'm going to take operations, elements of my operad. So this would be an element of my operad. This would be another element of my operad, and morphisms in that category are disjoint union of things coming from the operad. This is sort of what we have in I mean, in particular, if you try to read what this bit is saying in this definition, right? Good. So is this good? Well, what we see is the first thing we need here is an infinity category. And an infinity category means I already have defined something that composes up to all higher homotopies. So we have to start by having an infinity category, and the rule, I took a course on infinity categories a few months ago, and the rule number 1 I heard on infinity categories, so infinity categories is never try to construct one from scratch. Okay. Okay, never try to construct one from scratch. So what infinity categories are very good at is if you have some things, like for example, an actual category, or maybe several of these, and start doing constructions, then you can stay within the world of infinity categories. But if you don't have a category to begin with, which is our situation, we have a bunch of spaces and we know how to compose them, but the composition is not actually associative. Okay, it's associative up to homotopy, but this is not quite enough. I need to somehow argue somewhere that I have higher homotopies. Yeah, so I haven't, so this hasn't advanced me very much, because I'm still back at my, where are my higher homotopies, and how do I work out how to get them. Okay, so we're going to go back in time. We're going to go back 50 years ago. I'm going to, if among listeners, some people want to hear about dendroidal, I'm going to hop over dendroidal spaces, but I'm happy to talk about it in the discussion later tonight if somebody is interested. But I'm going to go all the way to 50 years ago. How did we, higher homotopies are not something new, something people were worried at the time the infinity operad was defined. How do we deal with this? Well, one standard method is this W construction of Bortmann-Vogt. I'm not sure I can do this. Anyway, okay, so the W construction is sort of a standard construction you can apply to an operad. I'm just going to say, well, if your operad P is the operad of associative algebra, operad of associative algebras, then it spits out a new operad WP, and WP is this A infinity, is going to be exactly the operad of A infinity algebras, and it has exactly this effect that, you know, what used to be, you know, when you have a P algebra, a WP algebra is going to be a P algebra to homotopy. It exactly encodes all the possible homotopies. Okay, so why is this useful? This is far too early. I have to see. I'm going to hide this very, very, very far away. Oh no. Okay. Sorry, we're not there yet. I need more space. We need more space. I don't know how much space I need. Anyway, go away. Go away. Good. Back to our W construction. So why is this useful for us? It's because there is an operad P, which I'm going to denote O, which is the operad of operads. So what does this mean? So this is an operad. An operad, it's a colored operad to be precise, but this is allowed here. A colored operad whose algebras are good old symmetric operads. Okay, so if I want an operad up to homotopy, if I'm asking, you know, what is an infinity operad in some sort of concrete way, you could say, well, a W, you know, W, so if I apply W, so WP, so WO in this case, this is an operad whose algebras are operads up to homotopy. And so these are by work of Berger, Sisinski, Mordek, but you can you know, or other people, WO algebras are infinity operads in today's sets. Okay, so if we are able to construct, if I can construct a WO algebra structure on my normalized cacti, then I'm done. So this is a concrete thing you can try to do. So what is the? So there's unfortunately a little problem. Is WO is complicated. Okay, so let me maybe try to give you an idea of what this operad looks like. So O was this operative operad. So O, yeah. So O is a colored operad, and so O is an colored operad, and what do with, you know, with elements. One way to depict elements in O is given by trees. trees. So, you know, when you think of tree T, if I give you a tree like this, and I have, you know, if P, you know, what does it mean that it acts on an operad? So if P is an operad, so, you know, I have to give you maps like this, where it's O of you know, because it's a colored operad, I have to, if I'm gonna, you know, I have to input, maybe let's not try to this. So if I have an what is the idea? The idea is if I have an operad, P is an operad, P is a bunch of operations and equal to 0, then, you know, how do I say that it's an operad? I'm going to say that, well, if I have a tree area operation here, I have an element x is an element in P of 3, and if I have an element here, y is an element in P of 4, and then some other element here, I have a, you know, this tree is giving me a way of composing them. So this is, every tree like this can be thought of as a way of composing operations. So x in P, I'm going to take elements x in P of 3, y in P of 4, and so on. So O is going to be, the operand O is going to be all the trees that you can draw in this way, and it acts on operads by, you know, a tree tells you how to compose operations, and then if you think through how, you know, composition in O is by tree insertion. So when I have such a tree like this one, it's a composition of operations, and if I have another little tree like this one, I could insert this tree inside a vertex of the correct arity. This is a little bit of a quick, rough idea of what the operad O looks like. And now when you do the W construction on O, the W construction on O is going to be trees of trees, where these are from, the first trees are from the W construction, and the second trees are from O. And the trees of the W construction, it's so you have, you know, depict an element. I'm not going to do a beautiful drawing, I don't know, something like this. And in each of these vertices, I'm going to put a tree. So the ones labeling the vertices come from the operad O, and the other ones, and the big tree comes from the W construction. And the ones from the W constructions, they compose by grafting, by putting these above each other, whereas the other one composed by insertion. Okay, so this is still pretty complicated. So yeah, so what we do instead is to construct, what we did is to construct an operad of infinity operad, which is less ugly. So let me take the statement now. We can go back up. And we can read this through. All right. technical issues. Okay, so what is our statement? So there is an operad which we call BO, which is an operad of bracketed trees. So the space, so if I have to give you for every, I'm going to have a collection of, yeah, this is not correct now, I see it. I was trying, so this, for every, so, okay, maybe I did it correct. Sorry. So O has inputs, K1, Kn. So in our operad O, I have to tell you what sort of, I'm going to input operations like we have. I was trying to avoid this, but this is not such a good idea. So this is an element, this one would be an element in O of, I have to label my vertices to know which, what order they come in, right? I mean, if I call them 1, 2, 3, and 4, then the first has arity 3, so I'm going to put a 3 here. The second has arity 2, I'm going to put a 2. The third arity 2, and the fourth has arity 4. Okay, so this is an, if I want to apply this element to my operad P, I'm going to take, I'm going to have to use an element of P of the P3, of P2, of P2, and of P4. Okay, so likewise, BO will be BO of K1, Kn. And what is it? Well, for every, so O is a discrete operad. For every element in this discrete operad, T, I'm going to take a poset of bracketings of the element, so of tree. So if of the tree. So if my tree is as I drew it here, then I can start putting brackets. And this is totally analogous to what we did with the A infinity operads. So when we were looking at A infinity algebras, we were saying, well, how do I talk about an algebra which is associative up to homotopy? Well, I'm going to look at all the possible bracketings of the algebra, and then and then I'm going to, I mean, you can formulate you can formulate the A infinity operad exactly in this manner. So if you had your tree, he would be, the pentagon. You would get it by, we're multiplying elements in a row, and we're going to bracket. We first do one multiplication, and then we do. I first compose these two guys together, and then I maybe compose these two guys together, and then finally I do the last composition. So the A infinity operad will sit there coming from the trees that are linear like this. But in general, when you compose operations in an operad, you're going to have a tree of how these operations are put side by side, and so you have a more complex. You have like polytopes of bracketings of trees where you can. I mean, these polytopes are always the nerve of a poset of bracketing. So this is a.
Nathalie, could I ask a question,
yes.
Please? Just to clarify. So I think, if I understand, the vertices are trees of trees. Is that right?
No, in WO.
Yeah, but also in B. You said that it's the nerve of the poset bracketing. So if I understand right, a vertex of the poset of bracketings is a bracketing, which is the same thing as a tree of trees.
Yeah, you can say. I mean, this is like so. This operad is closely.
Is what I said wrong? In fact, is it not the case that a bracketing is a tree of trees?
No, it's correct, right? I mean, it's a tree.
Okay, then, and so is it not correct that the vertices of BO are trees of trees?
Yeah, I think that's correct, right? I mean,
Okay,
that's
that's
exactly the relationship. You know, there is a map from WO to BO, right?
Well, that I don't know. I mean, we'll see. But yeah, okay. I'll have more. Sorry, I just wanted to make sure that I was understanding what the bracketings means. Okay.
Yeah. Yeah. So what? Yeah. So what we show is a bit. As I was saying, the sort of it's closely related to W. It's not actually equal to W. It's a smaller operad. In particular, because when we do these bracketings on a tree, we don't the W construction is something that resolves everything in the operad, including what corresponds to the symmetric group action. And we don't, in this bracketed version of O, we do not resolve the symmetric group action. So what will happen? So this operad comes with maps, which are operad maps, which are homotopy equivalences. So it's like, you can think of it as some sort of like WO is like the complete resolution of the nice cofibrant resolution of O. BO is something that sits in between, which is puts a lot of contractible stuff above every operation in O, but not absolutely everything. But in particular, every BO algebra is a WO algebra. So every BO algebra is an infinity operad in today's language. And if you unfold what the W algebra really is, a BO algebra really is, well, it will have an actual symmetric sequence. So it will be a bunch of spaces with actual, proper group action. I mean, actions of the symmetric group on the n space. So this is not resolved at all, which is the situation we were interested in, because our normalized cacti have such a symmetric group action. And then there will be a well-defined chosen composition, but the composition is only A infinity in some, it's going to be a homotopy associative up to all higher homotopy. So this is a way to encompass, to encode all these higher homotopies. And what we do is we actually construct a BO algebra structure on Cact1. So where we use these exact spaces and their natural symmetric group action, and we use this exact Cact1 composition that did not work, that only worked up to homotopy. So maybe sort of what's a very quick idea of how do you actually then construct these homotopies? So now we have an operad, which is the nerve of a poset. So for every tree, which is telling me a way of composing Cact1 operations, I am now also adding the data of in what order I'm going to do them. Maybe I have a full bracketing. If I have a full bracketing, then I know exactly what I want to do. If I have bracketed like 2 and 2, I mean, if I only use my brackets will only sort of compose one extra thing each time, then I'm going to use exactly this Cact1 composition that I have decided. So what we have to do is to use this sort of partially bracketed trees to define things that interpolate. And I mean, the very, very, very rough idea is sort of in, you want to, we reduce it to, defining, so, defining compositions via a parameter or via parameters in a rescaling, so a rescaling space. So these are the strictly monotone maps from the interval to each cell. So you should think of these as, there are some reparameterization of S1 fixing the base point. So we are sort of, these are, the homotopies you can show somehow, they can you can encode them in by choosing reparameterizations of this one, and this one, and this is a convex space. So once we have decided what to do with every vertex in this poset of brackets, then we can just linearly interpolate using this. I should stop here.
Thank you very much. Are there some quick questions?
Yes, I have a question. So I actually also have a comment, which is that B is the Dwayakhan resolution of the colored operad O.
B
is the Dwayakhan resolution.
Dwayakhan.
Yeah. So they introduced it for categories, but for multi-categories, it's, you know, it's a fairly evident adaptation of their construction. So it's just the simplicial resolution coming from. It's just, yeah. So Dwayakhan, it's I mean, one way of saying it is it's the simplicial resolution coming from the monad whose algebras are colored operads.
Yeah, I don't think it's exactly correct. I mean, it's close. You know, it's obviously close to a bunch of. It's also close to the W construction, right? It's not exactly the W construction. It's also if you do a monad, I think you will get. You probably you might get us closely related, but.
Well, maybe during the discussion you can show me an example of a simplex which is in one but not in the other, because I absolutely don't see any difference with the Dwayakhan construction. So I'd like to see. But you're saying
taking the monad and doing a bar resolution or something like that, right?
That's all I'm saying. Yeah, it was used by Ching, for example, in his thesis, but it's a well-known construction. The thing is that the Dwayakhan construction, it's by Berger and Moerdijk, at least in the non-colored case, it's geometric realization, which is is W. It's homeomorphic as an operad to W.
Yeah. So this one is not right. You have to be careful.
Yeah, so
two things is the symmetric groups. And it's very confusing because there are two symmetric groups going on, right? I mean there's the symmetric group actions of the algebras, which is not the same as the symmetric. You have the operad of operad, which is a symmetric operad, but its algebras are also symmetric operads. So there are two symmetric groups hanging around here.
Oh, you've got some. Oh, there are actual operations from objects in automorphisms in this operad.
Yes.
It's very unlike the A infinity operad, I guess. Yeah, which has no operations from an algebra to itself. Yeah, I've got a question. That was my comment. The question is, so the BV operad is cyclic, but the cactus, the normalized cactus, is certainly not cyclic. Any idea what one could do?
No, I don't know.
Okay.
No, I mean, it's a very sort of uncyclic. I mean, it's the same in this, where this comes from. This category of graphs is very asymmetrical in inputs and outputs.
Mm-hmm.
I don't know.
Yeah, because that asymmetry reminds me of a lot of string field theory work and then also a lot of work in mathematics that I know yeah, this comes up a lot. But the thing is, the beauty of the realization of BV, for example, as genus 0 Riemann surfaces, is that model is manifestly cyclic.
Yeah.
So it's a puzzle for me,
how
to see the cyclicity. Yeah. Thank you. Yep.
Maybe just a short other question. So you used as a model now for infinity operads these BO algebras.
Mm.
Do you now know, or do you have any idea of, could you modify this to get a model, say, as a dendroidal Siegel space or as a dendroidal set or something? Can you use some transfers to understand now what they would be in a different model?
Yeah, so I mean, what we did is, I mean, we wanted to, we started by trying to do dendroidal spaces because we thought that looked like a nice model. Then decided this was not so easy to use either. But what we have is a bracketed version of the dendroidal category. So the dendroidal category has, I mean, now it's again there are lots of subtleties, but the objects are trees now, and the morphisms are certain collapses and stuff, and but some of these interesting morphisms, the one that are sort of inner cofaces, are collapsing subtrees. Mm-hmm. Now you can do a poset of bracketing on the things that you collapse. And so what we show is that the category of PU algebras is equivalent to the category of appropriate Siegel of this version of a hat version of dendroidal spaces. And now you can rectify because this category is equivalent to the original dendroidal category. You can strictify such a thing to an actual dendroidal space. But then in the end you don't get something which is better than just taking the old Cactus opera to begin with.
Yeah, no, sure.
So this is not sort of, it's theoretically amusing, maybe, that you can bring this, but is this really, really useful? I don't know.
And I second your rule. I second your rule, by the way, about constructing
Yeah, I owe the rule of infinity category to Marcus Land. He taught me.
Yeah, thank you.
Since we still have a couple of minutes, I have a very naive question about this last slide. So you have those reparametrizations of the segment, and is it related in any way to this Thompson group?
Sorry? So I have these
Is it related, those reparametrizations, right? There is, as far as I recall, some famous group called the Thompson group.
Yeah, no, it doesn't. No, because where it's it's not completely unrelated, but I mean the basic the thing is you could. A cactus, instead of drawing it as a cactus, you can draw it as a bunch of here's one lobe of my cactus, and then maybe I have another lobe that goes here and then keeps going over here, and then this this would be the 1 and 2, and this is maybe a piece of 3, and this is maybe also a piece of 3, and maybe this is my lobe number 4. So it's you can just think of the outside circle. And so so these are subdivisions in this sense. They are subdivisions, and then we're going to do rescalings that that they'll take subdivisions to other subdivisions.
How is it to get the Thompson group? Isn't it true? You should probably just impose
the Thompson group. So the basic Thompson group. I mean, you have a version on the circle, you have a version on the interval, but the one on the circle you would do. You will do only certain rescaling. So, for example, so this is I divide by 2 and by 2. Yeah. So I'll do a map.
Can't you restrict your setup, the Cactus setup, to those divisions? So yeah, Thompson will only favor some divisions, some particular divisions.
Exactly.
Can't you restrict your situation to exactly those divisions in the Thompson group?
I mean, it's what you can say exactly what the situation is, right? Because you start with normalized cacti, so you start with things that are subdivided in n for different n's.
No, you're probably not allowed in Thompson. You would not be allowed to attach leaves where you want. But so what? Right? You would only be allowed.
No, Thompson. I don't think this is a problem at all. But the thing is, I'm going to use all sorts of fractions. But I don't just do subdivision by binary, or I'm not going to be. I'm going to stay within fractions. But how many, what the scaling is depends on the arity of the things I'm plugging in. Right?
Mm-hmm.
So it's definitely we are within a sub thing of we don't use all these monotone maps, obviously, but more than the Thompson group. Yeah.
Okay, thank you.